The second part of the lesson is the energy. So we know that energy exists in different forms, and so when anything happens around us, it is due to energy being transferred from one object from one form to another. We say that energy and work are related to each other because just like money gives us the ability to purchase goods and services, energy is the thing that is needed, or it gives us the ability in order to be able to do work. So let's see the different type of energy. We have two main forms of energy. We have the kinetic energy that is related to the motion, and we have the potential energy that is related to the store. So the kinetic energy could be light energy, sound energy, thermal energy, electrical, or kinetic energy. All of them, they represent the motion, or they represent a form of energy that is in motion, while potential energy is a stored energy. So chemical energy is stored in food, and next it's stored in our body, or it's stored in fuel in our cars. Nuclear energy is stored in the nucleus of the atom. Elastic energy is when you stretch something like a rubber band, or when you stretch an object and then you release it, the object will move due to the stored energy that was stored in the elastic material. So it's called elastic or strain energy. Last one is the gravitational potential energy, and this is the stored energy that is stored in an object because it's raised up against the force of gravity, pulling it downwards. Energy can be either stored in an object or transferred, as we said, and energy can be transferred by different forms, by applying a force, or by heating, or by radiation, or through electricity. So these are the main, if you want, type that would make us transfer an energy from one form or one store to another. So for the energy conversions, we need to know that energy cannot be destroyed or created. It's always converted from one form to another. It's transformed. An example of that is that if we have a car and we fill the car with fuel, so we have a chemical energy of around 1000 joules. The moment you start the engine, all the stored energy that was chemical energy will start to be dissipated to the surrounding into different form of energy. The car will start to heat up a bit, so it's a thermal energy. It will give a sound, so that's a sound energy. Okay, and imagine that we started the engine and we start to press on the fuel. If we have a hill, so the car will start to go up the hill. So we have both kinetic energy due to the motion of the car, and we have a gravitational potential as the car is moving upward or is raised upward against the force of gravity pulling it down. So as you can see, the 100 joules was distributed into the different forms of energy. But if we sum up all the different forms of energy after we started the engine, you will see that it's always gonna be the same amount. So the energy before and the energy after is the same because energy is conserved. But unfortunately, not all the energy after we start the engine is converted into a useful energy. Some is considered as a waste energy. In order to know how efficient an object is, we can use Sankey diagrams. A Sankey diagram summarizes all the form of energy transfers taking place in a process. They are usually drawn to scale. Okay, so the thicker the arrow means the greater the amount of energy. The useful energy are usually represented with a straight arrow, while the waste energy are represented with the curve. So they could be curved downward or curved upwards. And all the straight arrows represent the useful one. Okay, so in order to calculate the energy efficiency, we can use the formula useful energy out over total energy in multiplied by 100. In this case, if we want to calculate the energy efficiency of this lamp, which was provided with 110 joules of electrical energy, and it gives us 60 joules of light energy and 50 joules were wasted as heat energy. So we will divide 60, which is the useful, divided by the total, which is 110, and multiplied by 100, we will get 54.5%. This is the efficiency of the bulb that we have. So the bulb isn't very efficient, and heat is the waste energy dissipated to the surrounding. Okay, and this is why some objects they cost a lot of money. Like, let's say, I don't know, some kettles are really expensive while other kettles are not. So the reason behind that is that the very cheap kettles, they don't have a very high percentage of efficiency, so their cost will decrease. They won't be very expensive. So this is why it's better to always buy the devices with a better efficiency, and this is why they would be more expensive. But after all, you're saving money because you're using the same electrical energy and converting it to the energy needed for the device that you bought, because we don't want light or sound when we buy a kettle. We just want to heat up water. Okay, so some direct applications. If we have a light bulb that takes 30 joules, it transfers 3 joules as useful energy, so they did not specify what type of useful energy. And then we have 27 joules are heat energy. Draw the Sankey diagram. Again, remember that Sankey diagram is to scale, so you need to have the energy given, like the total energy should be the thick arrow. Okay, so that represents the total energy, and then any useful is represented with a straight arrow. Any waste should be curved upward or downward. Okay, and so this is the Sankey diagram: 30 joules in, 3 joules out as light, and 27 joules out as heat. Calculate the efficiency. Applying the rule, we will have useful over total divided by 100, and so the answer is 3 over 30 times 100. It's 10%. So this is a very insufficient, like it's not very efficient light bulb. We have a kettle that transfers 1200 joules of thermal energy stored in the water and 300 joules to the air as sound. How efficient is the kettle? So they gave us the energy that was transferred as 1200 as thermal, and 300 joule is the sound. Okay, so first thing, in order to calculate the efficiency, we will state the formula: useful over total times 100. Now, in such case, the useful energy is what? The useful energy is the thermal energy. Yeah, because this is why we buy the kettle, to warm up water. So the total energy N would be, we need to sum up the thermal energy and the sound energy to get 1500. Now, applying the rule, it would be useful out, so that's 1200 over total in, which is 1500 multiplied by 100, that's 80%. So this kettle would be actually expensive, as it gives you a good efficiency. Okay, question 3. We have a pendulum with a store of 2000 joules of GPE transfers to 189 joules to a kinetic energy store on its first swing. How much energy is being wasted due to friction by transfer to a thermal store? So in this case, friction is the waste energy. So in this case, the thermal energy is considered as waste, because this is what the pendulum, like it It's not designed for any reason actually. Anyway, so the waste energy in my case would be 11 joules. You just subtract 200 from 189. So how much efficient is my pendulum? Divide the the useful out by the total in. 100 times 100, you'll get 94.5%. These are the examples that you need to solve. I'm not gonna match the meaning of each energy. You can do it yourself and I'll provide you with the answer key. However, I'm going to solve the 3 boxes, the questions. So we have a team of university students that are testing a new car that they're designing. They find out that 3,500 joule of it is kinetic energy, 9,000 joule is transferred to heat, and they put in 12,500 joules of energy as fuel. Calculate the efficiency. So the energy efficient is the useful energy out over the total energy input in times 100. So the useful energy is the kinetic, as this is why they're designing the car to move. We don't need it actually to give us any heat energy. So the total energy is 12,500 times 100. So that will give us a 28% efficiency of their car. So their design isn't actually good enough. Second example, a television that is 83% efficient produces 4,600 joules of useful energy. How much energy does it consume? So knowing that energy efficient is equal to the useful over total times 100, we can rearrange the formula because this is what we need. So we will say total energy total is equal to useful over efficient times 100. And so by substituting everything given to us, we will get that the energy total provided to this television was 5,542 joules. Last example is a washing machine consumes 550,000 joules of energy, loses 315,000 joules of at the same time. What is the energy efficient? So first we need to get the energy useful. So what is the useful energy? Useful would be total minus waste, as energy is always conserved. So 550,000 minus 315,000, that's 235,000 joules. That's the useful. Again, applying the rule, useful out over total in times 100. I'm not gonna substitute the answers. You will get 42.7%. Okay.